let's take a look at this example. This time we have single-ended input and differential output. Okay, and we have to find ICQ, VCEQ, Zin, and Vout. So in order to find ICQ, again, I'm supposed to find VE. Why I have to find VE? Because I have to find the voltage across this resistor. Okay, so in order to find the voltage across the resistor, I need VE. VE is equal negative VBE. If you don't know why this is negative VBE, you're supposed to watch the previous videos. So this is negative, we'll assume this is 0.7 volts, negative 0.7 volts. Most of the time we are going to assume that the voltage between base and emitter is equal 0.7 volts if it's not specified different. Next, we're supposed to find VR3, which is also called VRE. This is nothing else, just VE minus VEE. This is equal negative 0.7 volts minus negative 18 volts. So VR3 is equal 17.3 volts. Okay, so this is the voltage across resistor R3. Next, I'm supposed to find the current which goes through resistor R3. So IR3 is equal also IRE. As I said, in some books you are going to see that this resistor is labeled IRE, and this is VR3 over R3, where VR3 is equal 17.3 volts divided by R3, 62 kilo ohms. Okay, we are going to use the calculator. We have 17.3 divided by 62 exponent 3. This is equal 279.03 microamps. Okay, so this is my tail current. Okay, tail current is the current which goes through this resistor. Next, we're supposed to remember that IE1 is equal to IE2. In general, we say this is IE, and this is nothing else, just half of the current which goes through resistor R3. So I write that IR3 divided by 2 is equal to my IE. So I have 279.03 microamps divided by 2. So I simply write that IE, let me remind you, IE represents my IE1 and IE2, is equal, I'm going to use the calculator, we have 279.03 exponent 6 negative divided by 2. This is equal 139.51. 139.51 microamps. Okay, so this is the current which goes through the emitter of transistor Q1. Okay, this is my IE1 and this is my IE2. Okay, IE represents these two currents. Next, I'm supposed to realize that the current which goes through the emitter is approximately equal to the current which goes through the collector of each transistor. Why? Because the base current is very small comparing with the values of IC and IE. That's why I'm going to write that IE is approximately equal to IC, and this is equal to ICQ. This is equal 139.51 microamps. Next, I'm supposed to find VCEQ. Okay, we found ICQ. In order to find VCEQ, I'm supposed to find VC first. VC is equal VCC minus IC times RC, where VCC in our case is equal 18 volts minus IC 139.51 microamps times 39 kiloohms. So VC is equal 18 minus 139.51 exponent 6 negative times 39 exponent 3 equals 12.55 volts. So this is 12.55 volts. This is my VC. Now I'm supposed to find VCE. VCE is equal to my VCEQ, which is equal VC minus VE, which is equal VC 12.55 volts minus VE, which is equal negative 0.7 volts. So VCEQ is equal 13.25 volts. Okay, so this is my VCEQ. Next, I'm supposed to find the input impedance at my non-inverting input. So I have first the formula for small re, AC emitter resistance, which is equal 26 millivolts over IE. So I have 26 millivolts divided by IE 139.51 microamps. 139.51 microamps. This is equal. I have 26 exponent 3 negative divided by 139.51 exponent 6 negative. This is equal 186.36 ohms. Okay, so this is the resistance, okay, AC emitter resistance RE. Next, in order to find Zin, I'm supposed to use the formula. Zin is equal 2 times beta AC times small re. In our case, we have beta equals 250. If it's not specified, if this is DC or AC, I assume that beta DC is equal to beta AC, and this is equal to 250. That's why I'm going to write that this is 2 times 250 times small re, 186.36 ohms. Okay, this is equal. I'm going to use the calculator. So I have 2 times 250 times 186.36. This is equal 93.18 kiloohms. So this is the input impedance at my non-inverting input. Next, I'm supposed to find the output voltage. In order to find the output voltage, I'm supposed to find the differential gain of my differential amplifier. So the formula says the differential gain is equal RC over small re. We have this formula for the configuration called single-ended input and balanced output, okay, because we are going to get the output from the two collectors of my transistors Q1 and Q2, okay. So this is my differential output, single-ended input, differential output. So my RC is equal to R1 and R2, which is equal to 39 kilo ohms over small re, 186.36 ohms. This is equal, I'm going to use the calculator, we have 39 exponent 3 divided by 186.36. This is equal 209.27. So my differential gain is 209.27. Please keep in mind that in our case we use the notation AD, which stands for the differential gain. In some books we are going to see AV, voltage gain. It means exactly the same. Next, we're supposed to find the output voltage. In order to find the output voltage, you're supposed to remember the formula, which says that differential gain is equal V out over V in differential. Okay, where we have V out over the differential input voltage, which is nothing else just the voltage at the non-inverting input minus voltage at inverting input. Okay, so this is my differential input voltage. If you are going to use the algebra, you will find that V out is equal the differential gain times the differential input voltage. Okay, so we have VNI minus VI. This is equal, we found that differential gain is equal 209.27 times the voltage at the non-inverting input is equal 3 millivolts, and voltage at the inverting input is equal 0 because that input is connected to the ground, and this is equal, we have 209.27 times 3 exponent 3 negative. This is equal 627.81 millivolts. Okay, and this is my output voltage. Of course, this is peak because we applied peak voltage to the non-inverting input. So at this moment we can say that the problem is solved.